So as I mentioned before, the idea of simple harmonic motion, the pattern of motion that we see and how it connects position, velocity, acceleration / net force, and time, all really results from one relatively simple phenomenon. And that phenomenon is something that we call a linear restoring force. So I'm going to present to you the thesis that a linear restoring force is what's responsible for simple harmonic motion. We'll accept that for now. We'll come back to it next week. What I want to show you today, though, is what a linear restoring force is, and we're going to work through some evidence that shows that the two systems that we're going to be looking at, which are pendulums, you've already been investigating, and systems with springs and masses, those are both systems that exhibit linear restoring forces. First we got to figure out what a linear restoring force is. Then we're going to talk about springs. We haven't talked about those yet, but we're going to. And I'm going to show you how those can be thought of as characterized by linear restoring forces. And then we'll talk about pendulums, which are a little bit more complicated. Yeah?
What systems in nature have linear restoring forces?
So that's a great question. I think realistically, the kinds of things that we see with linear restoring forces are not necessarily things that we see in nature. There are a few things that we would see. So if you have like the vibration, like the motion of a tree in the wind is a really good example. So if a tree starts moving, it will move with something very close to simple harmonic motion, right? And we do see in nature things like vibrations of vocal cords and things like that that are examples of simple harmonic motion. But mostly what we're interested in is human systems, not necessarily nature, but there are examples of it. Okay, so to talk about a linear restoring force, we have to make one thing really clear, and that is that we are not talking about forces that change linear with respect to time, because they don't. What we're talking about is forces that vary with some displacement. Okay, so if we have an object and it's located at a certain point and it's experiencing no force at all, but it moves farther from that point and it experiences a greater and greater and greater force, and the farther it goes, the greater the force, and the amount of force increases as a linear function of how far away that object is from that position. That is a linear force. A linear restoring force is one where no matter which direction you move away from that equilibrium point, the force will push or pull you back. So if you move farther one way, you'll experience a force in the opposite direction that increases linearly with time. If you move the other way, you'll experience a force that's in the opposite direction of your motion that increases linearly with time as well. So no matter what direction you move, there's always a force pushing you back toward the place where you weren't experiencing any force, and the farther you go, the greater the force is, and that increase in force is linear. All right, so with time, that's not necessarily true. If we were to watch an object moving, we might see that it moves to one position really quickly and then stays there for a while, and then slowly moves to the other position and then moves really quickly all of a sudden, and it stays there for a really long time. We're not saying that the forces are changing in a linear fashion with time. All we're saying is you put the object here and it will have a force that corresponds to a linear function of that position. And when we have objects that are characterized by linear restoring forces, systems that are characterized by linear restoring forces, then we will see simple harmonic motion. This I'm not going to prove today. We're going to dive into this next week. What I want to do today is just make sure that the systems we're looking at actually do have linear restoring forces. Once we've established that, then we can take those linear restoring forces and think about how can we use that to prove that the position, velocity, and acceleration will all be functions of, will all be sign functions with respect to time, okay? So let's start by thinking about springs, and we'll start by thinking about what like kind of the easiest situation is. If you have a spring, it's just sitting there, then it's not exerting any forces. And if we set it up so that it's pushing on something, or that there's something next to it, but we don't squish the spring or stretch the spring at all, then the spring is exerting no force at all. If we start pushing the object one way, the spring will push back. If we start pulling the object one way, if the spring is attached to it, the spring will start pulling back. So there's a restoring force. And it turns out that that restoring force is going to be linear with respect to the position of the object. This equation right here, the force exerted by a spring is equal to negative kx, is called Hooke's law. K is what we call the spring constant. And you'll see an example of this in just a second. And we've looked at this a couple of times. We looked at this indirectly when we were looking at elastic potential energy. And we talked about it just the tiniest little bit with that. But you looked at it in more detail back in the fall with Mr. Ayer. Mr. Ayer had you all hooking masses up to rubber bands, remember? And then measuring how far the rubber band stretched. And when you made a graph, what you saw is, oh wow, the larger the weight, the larger the stretch, and it was proportional. If you hung a mass of certain, hung a certain mass, you'd get a certain amount of stretch. If you double that mass, you get twice the stretch. So effectively what we're saying is there is a linear relationship between the force exerted by a spring and its stretch or squish. We call the stretch or squish deflection. And it doesn't matter which one we're talking about. You get the same amount of force either way. If you pull it 1 centimeter, you get the same force as if you squish it 1 centimeter. And since the direction is always opposite of the way that you've moved relative to the equilibrium point, if you pull it away from the equilibrium point, the spring will pull back. If you push it away from the equilibrium point, the spring will push back. Then it's a restoring force. So we can see that a horizontal spring is going to be a linear restoring force. And this is what the graph of force versus position looks like. If we have the object and it's not pushing or pulling on the spring at all, there's a force of 0 newtons. If we say this direction, you're right, is the positive direction, then if we pull the object in the positive direction and stretch the spring will pull back in the negative direction. And the amount that it pulls will increase linearly with distance. So if the displacement, the deflection is positive, then the force is going to be negative. If we push our spring this way, now our deflection is negative. We're moving the spring and the object in the negative direction, but the force is pushing the other way. So for negative deflection, we get positive forces. And that's what gives us this equation, negative kx, because the force from the spring is always opposite the direction of the deflection. This slope here is the spring constant, and it's going to reflect, the magnitude of that will reflect the force exerted by the spring divided by the deflection. For what we call ideal springs, that's a constant. Real springs aren't ideal. As you start getting to the extremes, when you stretch a spring really far, it stops being linear. Or if you squish it too far, it stops being linear. But there's sort of a sweet spot for most springs in which it is virtually linear. And this is not with respect to time. We could take a spring and squish it 3 centimeters. Now it's squished 3 centimeters. So we have a 3 centimeter squish and a resulting force, and it's not changing. Time is going by and it's not changing. I can squish it slowly or I can squish it quickly. this graph tells us nothing about time. If we were to take a spring and pull it and then slow down and stop, and then squish it and slow down and stop, and then pull it and slow down and stop, then what we would see is on this graph, the force versus position would kind of track like this. We pull it and then slow down and stop, and then we squish it and slow down and stop, pull it and slow down and stop, squish it and slow down and stop. So we could think about what's going on here in terms of both force and position in terms of time. And they would track with each other, but we can't get anything about time from this graph. The only thing we can see here is that it's a linear restoring force. Okay? So with a horizontal spring like this, if we were to see simple harmonic motion, what we would see is the object going back and forth and back and forth and back and forth in much the same way that your pendulums were swinging back and forth. That characteristic fastest in the middle, slowest at the ends motion. The problem with this is, as you can see, if we have a spring moving horizontally, it's going to be sliding along a surface. And if it's sliding along a surface, then there's going to be friction that we have to deal with. So it actually turns out that it's much easier to think about spring motion in terms of a vertical spring. If we take a vertical spring and we hang something from it, then there's no friction. And we can easily get simple harmonic motion just by kind of bouncing from the spring. The problem with that is that we've introduced a different force, which is the weight of the object. Now we've got two forces acting on the object. The spring may be pushing or pulling on it, or maybe not. Maybe the spring is exerting no force at all. And the gravitational force is pulling on the object straight down. One of those forces is changing, one of them is constant. So now what do? Well, it turns out it's actually really straightforward. You do not have to write all this stuff down. I'm going to walk you through it just because I like math, and I know some of you like math as well. But what we're going to end up with is something super simple. So here's how it works. If we take an object and we hang it from a spring at its equilibrium position, the weight is going to be equal to the force from the spring. There's no net force. The force from the spring is going to be K times the deflection. If we call the deflection at that equilibrium position L, then the overall force on the spring is 0. The downward force from gravity is mg. The upward force from the spring is KL. So KL and mg are going to be the same. If we then push this object up, so here's my equilibrium position. If I push it up, I am decreasing the force from the spring. The force from gravity is the same. So I've dropped the force from the spring. How much is the spring pushing on it now? Well, if I think about where it was at position L. And if I lift it up y from there, then the new position is L minus y. And that position times k will tell me the force from the spring. So the new force from the spring is k times L minus y. And that is the upward force. The downward force is the weight. And the difference between those two things is going to be the overall force on the object. But we already figured out that k times L is mg. So if we just distribute this k and then move mg around, what we see is the net force is going to be KL minus mg minus k times y. And KL is mg, so that's mg minus mg, and what we end up with is the net force is going to be equal to the spring constant times the change in position from the vertical equilibrium position. So in other words, this spring is going to behave exactly the same way that it did before when it was horizontal. The only difference is the equilibrium position isn't going to be the unstretched spring. The equilibrium is going to be the spring stretched by just like however much it takes to balance out the weight of the object. And so, so this again is going to be a linear force. The net force on the object will always be a linear restoring force, or it'll be 0. And so since that's a linear restoring force, we can look at springs either horizontally or vertically. It doesn't really matter which way we do it. Pendulums are a little bit trickier, and I'm going to go through this more quickly than would do it justice, but it's a really neat idea that I want you all to see. So if we're looking at a pendulum, we've got a problem. And the problem is that the net force on the mass that's swinging back and forth is not changing in a linear way as a function of position. If we were to evaluate the net force at any one, say, angle being the string relative to perfectly vertical, then what we would see is as that angle increases, the overall force, the net force, increases. So far so good. And it's a restoring force, because no matter which way you go, that force is going to tend to move this object, be accelerating this object toward its equilibrium position. The problem is the magnitude of the net force is not linear with position. If we look at the gravitational force as having two components, one in the same direction as the string, and one in the perpendicular direction to the string, what you'll see is since this object isn't accelerating toward or away from the attachment point, the tension in the string and the weight of the object are balanced forces, and the net force is simply the perpendicular component of the gravitational force relative to the string. Okay? And so that is going to be related to the sine of this vertical angle, and that means that the further you go, the greater it gets, but it's a sine function. So from here, it goes up really fast. Now it's going up slower, slower. So now it's hardly changing at all because sine functions are very small at those vertical angles. So what ends up happening here is that we end up with a system that is not characterized by a linear restoring force, which means pendulums don't exhibit simple harmonic motion. Yeah?
And does that mean that it would be similar except that instead of moving in a line it goes along the arc length?
Well, not really. It's still not going to be linear is the problem. Because if you look at the magnitude of the force, it's not increasing with displacement in a linear fashion. It's increasing as a function of the sine of the angle, which is a smaller and smaller number as that angle gets smaller and smaller, right? So, if we make one little rule that's not difficult to make and not difficult to keep, if we think about motion that is mostly at real small angles, so angles of less than like 20 or 25 degrees relative to the vertical, then it turns out that most of the motion is horizontal. Just like if we were to look at a circle like this and think about, well, if we start here and we move to here along the circle, most of that change in position is vertical. The sine of this angle is going to tell us most of its motion. The cosine of this angle is going to tell us very little of its motion. It moves a little bit to the left, mostly it moves up. For small angles, that's generally true. And that's called the small angle approximation. And we can mathematically figure out, like, it's not accurate. It's never accurate. It's never 100%. But as it turns out, it is so close that for most applications, the sine of an angle is the angle if we measure our angle in radians. Okay? If you measure your angle in degrees, the small angle approximation still works, but then the sine of the angle won't be equal to the angle. The sine of the angle will be equal to something close to like 2 pi divided by the angle or times the angle or something. So we're going to be 2 pi times the angle divided by 360. So we'd have to do a little bit of conversion. What we're really saying here is if you look at a sine function between relatively small angles, it is basically linear. This part of the sine function is linear. And it's only when you get into angles that are greater than about 10 degrees that you start seeing a deviation from linear. So if we work with angles that are somewhere in here, we're good. This is showing half a radian, right? And that's, we can't even tell looking at this graph. Half a radian is virtually identical to the sine of half a radian. And if you get your calculator out, you can see this. You don't have to though, I'll do it for you. If you take a calculator and you do some calculate, you gotta make sure you're in radians, so I'm in radians right now. If I find the sine of say 2 radians, then I get 0.909. If I find the sine of 1 radian, then I get 0.84, that's closer. But if I start looking at real small angles, like 0.4 radians, 0.4 radians has a sine of 0.389, that's almost 0.4. 0.2 radians has a sine of 0.198, that's basically 0.2. 0.1 radians has a sine of 0.0998, that's basically 0.1. The smaller you get, the closer you get to the sine and the angle being the same. The sine of an angle is the same as the angle in radians if the angle is smaller than about 10, 15 degrees. So if we use that trick and we say that we're not gonna take our pendulum and move it up past about here, then what ends up happening is the arc motion of this pendulum is effectively the exact same as its back and forth motion. As we get towards the end, it's moving a little bit up, but not much. Mostly it's moving left to right. So as long as it's moving only left to right, then the sine of the angle in radians will be equal to the angle, and that means that the force will be proportional not to a sine function, but to a linear function. As that angle increases linearly, the force will increase linearly. That's linear, and that means that we can use that to determine the magnitude of the force acting on a mass at the end of a pendulum string. And it's related, so theta is defined as the arc length divided by the length of the pendulum. So basically what we're saying is that theta, which is S over L, times mg is the magnitude of our restoring force. So if we know the horizontal displacement of the pendulum, the length of the string, and the weight of the mass, we can determine the magnitude of the restoring force. That will be a linear function. So pendulums should show simple harmonic motion. All right, so that means that horizontal springs, vertical springs, and pendulums will all show that characteristic of a linear restoring force. And I am proposing to you that if we have a linear restoring force, then we will see simple harmonic motion. So we're going to stick to studying those systems. For the rest of the period today, what I want you to do is play around a little bit. I know we've just got a few minutes, but use the time. There's a simulation. If you go to today's module, there's a simulation called, well, it's springs, and there's some stuff to kind of look at and think about. On Monday, we're actually going to pull out real springs and hook up real masses to them. So it's to your advantage to kind of play around with this now for the 5 minutes that we have left in class. And I'm going to stop the video and see if there's any questions before you get started.